In this session, let us focus on the topic degree of freedom of different systems. This session is going to be helpful for any physics student who is trying to increase his understanding on this topic, as well as for anyone who is preparing for CSIR NET, GATE, TIFR, JEST physics exams. So let's get into the topic. First of all, let's define degree of freedom. Degree of freedom in classical mechanics, it is defined as it is the number of independent variables this is very important, variables should be independent, required to describe the dynamics of the system. Instead of dynamics, you can also use the word configuration. Now, by configuration, we mean where everything is. For particles, it means their exact positions in space, and for a rigid body, it means both location and orientation of the body. Now you know the definition of degree of freedom. Let's calculate the degree of freedom for different systems, starting with the simple pendulum. In a simple pendulum, we have a rigid ceiling. This ceiling is rigid here, and this is a string of length L, and it is constant, it is inextensible. One end of the string is connected to the ceiling and other end is connected to a bob. Now when we displace the bob from its equilibrium position by a small amount, it goes on to and fro motion. It swings away and toward the equilibrium position due to gravity. Now to describe this system's configuration, we can use x and y. To describe the horizontal position, we can use x, and to describe vertical position, we can use y. But since the length of the string is constant, we can write x square plus y square is equal to L square. So the value of x and y are not independent. Therefore, the number of independent variables is only 1. X is depending on y, which means there is only one independent variable. Therefore, degree of freedom is equal to 1. Now, instead of using two dependent coordinates x and y, we can use a single independent coordinates, which is theta. Theta is the angle made by the string with its equilibrium position. And now we can write x is equal to L sine theta and y is equal to minus L cos theta. And do not think L is a variable, L is constant. So by using only theta, we are now able to describe its horizontal position, its vertical position as well. The independent coordinates that we use to describe completely the configuration of the system, they are also called the generalized coordinates. So theta is the generalized coordinate in the case of a simple pendulum. Now there is a general formula for finding the degree of freedom, which is degree of freedom is equal to dn minus k. Here d is the dimension, n is the number of particles, k is the number of constraints. Let's see if this formula works in the case of a simple pendulum. In the case of simple pendulum, the motion of string is restricted to 2D. It only move in a vertical plane, so it is 2D. So D is equal to 2. And number of particles in a simple pendulum is 1. There is only one bob, so N is equal to 1. And number of constraint is 1. Constraint is restriction. In the case of simple pendulum, the restriction is x square plus y square is equal to L square. This is the restriction in the case of simple pendulum. So number of constraints is 1. So according to the formula, degree of freedom is equal to 2 times 1 minus 1, which is equal to 1. So this formula is working. Now let's move on to the second example, where we have a particle moving on a sphere. Particle moving on a sphere. So this is the particle. Its position can be specified by using x, y and z coordinates, but all of the x, y and z are not independent because these are related by the equation x square plus y square plus z square under root is equal to r. So r is the radius of the sphere. Again we can check if the formula of degree of freedom is working or not. Degree of freedom is equal to dn minus k. D is 3 here because this is 3 dimension. Sphere is in 3 dimension. And number of particles is again 1. There is only one particle. Minus number of constraints is 1, which is root of x square plus y square plus z square is equal to r. So degree of freedom is equal to 2. So out of x, y and z, only 2 of them are independent. The third coordinate depends on the other 2. Through the constraint, root of x square plus y square plus z square is equal to r. Now if you do not want to use an extra coordinate, you can use generalized coordinates, which is theta, phi in this case. You know that in spherical polar coordinates there are 3 coordinates r, theta and phi. R is a constant here because particle is at a constant distance r at any point from the center, and only changing variables is theta and phi. So to completely specify the system, we do not need 3 coordinates, we only need 2 coordinates, which are theta and phi. This is the generalized coordinate for particle moving on a sphere. Generalized coordinates. Now let's move on to the third system. In this system, we have 2 particles, a rigid body consisting of 2 particles. Now the definition of rigid body is the distance between any 2 points or any 2 particles in a rigid body is constant. So this distance, it is constant. Let's say it is L. This is equal to constant. This is particle 1 and this is particle 2. The distance between them is constant because that is the definition of rigid body. So here we have a rigid body of 2 particles. Now particle 1 can be specified by x1, y1, z1. Particle 2 can be specified by x2, y2, z2. The constraint is x2 minus x1 the whole square plus y2 minus y1 the whole square plus z2 minus z1 the whole square is equal to L square. Let's say this is in 3D, a rigid body of 2 particles in 3D. So degree of freedom is equal to 3 into, this is the dimension, times number of particles, which is 2, minus number of constraint, which is 1. So degree of freedom is equal to 5. Now for an n particle rigid system, it may be difficult to find the number of constraints, and therefore we use an already developed formula for finding the degree of freedom. Degree of freedom is equal to, this is in d-dimensional space. For an n particle rigid system, we have degree of freedom is equal to d into d plus 1 divided by 2. Now let's do a degree of freedom question which was asked in GATE 2021. In this question we have a hoop of mass m and radius r. It is rolling without slipping along a straight line on a horizontal surface. Also there is a point mass inside the hoop which is performing small oscillations about the mean position. We are asked the number of degrees of freedom of the system. Now we know the definition of degree of freedom. It is number of independent coordinates required to define the configuration of the system. So to define the configuration of this system, we need one coordinate to represent the translational motion of the hoop along the horizontal surface. Let it be x. So this corresponds to 1 degree of freedom. Now the hoop is also rotating about its center as it rolls without slipping. To represent the rotation we can use theta, but theta is not independent, theta is dependent on x. Theta is equal to x divided by r because this is rolling without slipping. So because of rotation there is 0 degree of freedom. Now to represent the oscillatory motion of the particle inside the hoop, we need another coordinate. So this corresponds to 1 more degree of freedom. So total degree of freedom is equal to 2. One is corresponding to the translational motion of the hoop and the other is corresponding to the oscillatory motion of the point mass inside the hoop. The rotational motion of the hoop is dependent on the translational motion of the hoop, therefore it does not add to the degree of freedom. Thank you for being here. If you found this video helpful, don't forget to like. Also consider subscribing this channel. Also comment the topics that you are struggling to understand and give your suggestions as well. That's all. Thank you.